Sure. Okay. Hi, everybody. Welcome to the annual OSL Virtual Town Hall. I hope you are in the right place. Um, I'm Larry Gritz from Sony Pictures ImageWorks, and also coincidentally the ASWF TAC chair this year. My co-presenters are Chris Kula from Epic Games, Alex Conti, also of ImageWorks, and Curtis Black, joining us by recording from Animal Logic slash Netflix Animation. Yeah, let's advance. This is part of the Open Source Days presentations. There are a number of other events over a few days that we want to let you know about. Next slide. This may seem a little bit behind the times because you may notice the OSL Town Hall is basically the last. So if you're seeing this slide for the first time, you've probably missed the other presentations, but I went to several of them and they are great. And the recordings of them will all be up on YouTube at some point in the coming days or weeks. So for those other projects that you might have missed the virtual town halls, but you're interested in the project, I do encourage you to go back and watch for them when they come up. Next, please. Then on this coming Sunday is the main schedule of ASWF Open Source Days talks. These are free. You don't need to be registered for SIGGRAPH, but please do go to aswf.io and register for this event. This helps the planning and also gets you access to the beers of feather. I don't think they will let you do that if you're not pre-registered. But this slide does call out that in addition to many interesting talks, we do have these 3 extra exciting keynotes that should be awesome. Next slide. And then following, right, so this is the rest of the schedule. I do not expect you to read it all here. You can find these on aswf.io. There's a prominent link to get to the open source days, and you can view the whole schedule. Lots of stuff on Sunday, and then these are the Monday sessions. Note about this, the Sunday sessions are free to attend, and they will be recorded and made available later. These Monday sessions are official SIGGRAPH Birds of a Feather meetings, so you do need to be registered for SIGGRAPH at some level in order to actually attend. They'll probably be checking at the door. And these, unfortunately, will not be recorded or streamed. So if you are interested in these meetings, you do need to come in person. And they are also great. Next slide. Okay, back over to Chris. Thanks.
Yeah, thanks, Larry. So welcome to the Open Shading Language Virtual Town Hall. In case you're wondering why you're here, what we're going to be talking about, just kind of give you the brief intro and spiel about what Open Shading Language is. It's first and foremost, a shading language that's designed for artists to describe materials, and it's really tailored for modern production renderers. It's already been integrated into lots of popular renderers and DCCs. You can see a brief list here that's not necessarily complete. It's both in several commercial packages. It's also used in several proprietary production renderers, such as Sony ImageWorks' renderer and Netflix Animation's renderer. And in addition to the description of the shading language, the OSL project is an actual open source compiler and runtime that works on both CPUs and GPUs for this language. Here are some recent projects that we're using OSL. These are, just a snapshot. OSL, again, is integrated into lots of products, so there's probably many beyond these that we don't even know about. So if you have recently used OSL on a project, we'd love to hear about it. Give you a brief timeline of the project, a little bit of the history. Back in 2008, the project started at Sony ImageWorks. The goal was to add a shading language for the in-house renderer there at the time. And it was really designed from the ground up to work well with path tracing in mind and physically based methods. Interestingly, the project was also designed to be open source from the start. We had been in contact with other studios, other renderer developers. We knew there was kind of a need for shading language implementation that would be open source, and we kind of thought this might be a good opportunity for collaboration. Uh, in 2010, we first presented it at SIGGRAPH. Around that time, LLVM became the main backend for executing shaders on the CPU with just-in-time code compilation. And from then on, the project became integrated more and more renderers. In 2017, it was integrated, it was recognized, sorry, with a scientific and technical award from the Academy. And in 2020, it joined the Academy Software Foundation. And this is great because it provides kind of a neutral platform where engineers can get together, discuss the project on a biweekly basis, and it's been great for coordinating all the contributions from different studios moving forward. So the OSL Technical Steering Committee is made up of a few folks listed here. Larry acts as the chief architect. I'm there mainly as a TSC chairperson, and everyone here on this list contributes to this discussion and evolution of both the language and the actual open source implementation of it. So OSL as open source specifically, like what does it include concretely? There's OSLC, which is the command line compiler. This is what an artist would interact with to verify that their shading code is valid and turn it into a form that's consumable by the renderer. This is not just a command line tool, but it's also available as a library, so you can fully integrate it into UIs. There's libOSLQuery, which is a small library, very lightweight, and lets you do runtime inspection of compiled shaders. So lets you, for example, build UIs programmatically from shaders that other people have written. You can query the parameters, input and output, and so on. Uh, libOSLexec is really the meat of the project. This is our big LVM-based runtime. It works for both CPU and GPU. There's three different backends at this point. The original backend, which shades one hit point at a time and works for both Intel processors and ARM processors. There's a CPU backend that's designed for batched execution. So this shades multiple points at once and can leverage SIMD instructions, in particular, like on Intel AVX2 and AVX512 instructions. And finally, the CUDA kernels. So OSL can generate a kernel with PTX instructions and turn that into code that can be executed on NVIDIA GPUs. And you'll hear more about other backends that are in the works going forward. In addition to this, we have a few testing harnesses. So we have test shade, which is kind of an example, the simplest example you can write of shading a grid of points to produce an image. We have test render, which is a small path tracer. It's really not meant to be a production renderer, but just to showcase how you would actually integrate this into a real renderer. And then OSL Toy, which is kind of inspired by Shader Toy. It's a small app written in Qt, and it's basically test shade with a small UI in front of it. So you can type code on one side and see the result in a window in the other. So what are some of the unique things that are different about OSL? The first is that shaders can be written individually and then be assembled into networks. So networks are evaluated lazily, which means that if you have a very large complex network that describes a material, any unused section of the graph is not actually evaluated. The other thing is that the runtime makes sure that the entire graph is runtime optimized. So that means different nodes that were written maybe even by different users, different artists can the optimizations can flow across nodes. So if you have, for example, a color correction node that's inserted after a texture lookup, and that texture, that color correction happens to be disabled, it'll be optimized away, even in a very large production network. And in practice, we've seen cases where the optimizer can remove upwards of like 98% of instructions. So this is really great for production shaders, which tend to come with lots of bells and whistles, but they're not all turned on at the same time. So you can have the benefits of flexibility and then also runtime efficiency. The OSL runtime also does automatic differentiation, so it tracks the proper signals to let you do filtering and bump mapping in a very accurate way. It's better than what was done kind of in previous generation systems that just did finite differences. This actually works even if you just have one shading point and works, in loops, in conditionals, and so on. And finally, another big design point is that shaders are designed not to compute colors, but to return closures. So that leaves the renderer in charge of how to integrate the lighting. And this is what lets OSL work really well with path tracers that typically want to reason about BSDFs, subsurface scattering, and other kinds of material properties with a more symbolic representation. And this also lets us do complex layering effects by building trees of closures. And you'll hear a bit more about some of that later today. Another question we get asked a lot is, how is OSL related to Material X? Material X is more of a higher level project, and it's really aimed at material interchange. So for example, how to bring materials across DCCs, across renderers, and so on. On the other hand, OSL is really a runtime that's meant to live inside a specific renderer. So the Material X library is taking material graphs, and it can produce OSL actually, but it can also produce code for other shading languages, for example, for real-time uses, so GLSL, HLSL, and other languages. But both projects definitely cooperate very closely. We work together to kind of establish best practices, best standards. So for example, MaterialX adopted OSL's definition of noise functions. OSL adopted MaterialX's definition of BSDFs and EDFs and layering operators. And then test render has been kind of a useful tool for both projects because it has a reference implementation of most of the Material X closures, and that lets us do some unit testing on both sides actually of both projects. And with that, I'll hand it over to Larry, who's going to tell you about what's new in OSL this year and going forward.
Thanks, Chris. Oh, you know what? I was looking at the slide when you were talking about the libraries, and just for the sake of completeness, there is actually one other library that comes with OSL that is worth mentioning, which is that there is a libOSL noise, which it's like a small mostly header library that is the full implementation of all the different noise varieties that that OSL uses internally. So that makes it really easy to pull into other renderers, even ones that don't use OSL at all, if you want to match those noise functions. So that's kind of cool. Sorry, just throwing that in. We can go back. Okay, so yeah, so this is our once a year town hall. So I think a big part of that is kind of recapping what the advancements have been over the past year. And so for us, the one big major software release that we did since the last time we had the virtual town hall was this past spring. We released OSL 1.14. It had actually been over a year since the previous major release. So it had a good overdue batch of advancements. So on the sort of, with any project of this scope, like a lot of the ongoing maintenance is about builds and juggling dependencies and fitting into other parts of the software ecosystem. And that's especially true for us. We have some complicated dependencies, especially because of our use of LLVM, which is not a lightweight thing to pull in. So this particular release pushed forward a lot of the minimum versions required of dependencies and other parts of the tool chain. So this brought us up to C++ 17 standard. We finally phased out Python 2, and we're fully on Python 3, starting with 3.7. And we pulled a bunch of the other dependency libraries in, notably LLVM up to a minimum of LLVM 11. I think we made a lot of people happy by finally fully eliminating the dependency on Boost. Not that there's anything bad with Boost per se, but it's a big thing to pull in as a dependency for the tiny pieces that we were still using. And it got in a lot of people's way. So we came up with substitutes for the few remaining things that we were using from that library. We also added, like those are minimum dependencies, but we also pushed the support for newer versions of a lot of our dependencies forward. Some of these are no small tasks, but with the initial release of 1.14 OSL, we added support for LLVM 18, and in subsequent patches since then, we've added support for 19 and 20. We brought support up to the current OpenImageIO 3.0, and also we keep close tabs on its main development branch also, so it will release 3.1 fairly soon, and we're already ready for that. And we are also clean for the latest versions of GCC, and if you wish to, compiling with C++ 20. We also, it used to be for a long time that the OSL documentation, like of the language itself, was a big PDF. It was actually written in LaTeX, boiled down to a PDF and distributed with the software, but we have switched to an online format via Read the Docs, but just as a shorthand, that's accessible through docs.openshadinglanguage.org. So that's just a much nicer thing. It builds automatically with every release, so it's always up to date, and you can compare to previous versions on the website. And another big advance that we had recently is through the many people's help, but also the ASWF organization's ability to pay for paid GitHub runners with GPUs. All of our PRs, when they go through continuous integration, now actually test against build supporting optics and running the full test suite with GPUs. So that's really great. It helps us verify that every change that we make is definitely gonna not break anything about the optics paths. Next slide, please. Great. Also, in terms of features and internals, so highlights from that release and work over the past year was that the texture calls have been augmented to accept optional color space information as optional keywords, so it doesn't break compatibility with any of your current shaders, but you can use that if you want. There have been a number of enhancements, largely because of Chris, but also contributions from NVIDIA on the test render test harness, which is, like Chris said, it's not meant to be a production renderer. It's mainly used for our unit tests, but you can use it for a lot of other interesting things too. But we have this past year added support for triangle meshes, displacement shading, and sort of a full overhaul and support of optics through test render. We also changed a bunch of things that users, like shader programmer users of OSL, will not need to know about, but the kinds of people integrating it into renderers will. And so from the renderer standpoint, one change that we made is all through the renderer services interface, which is like, this is the main way that OSL needs to ask for things back from the renderer for things that are implemented on the renderer side or information that it has. All of those things that were UString based have changed to UString hash. And there's an interesting reason for this, which is that as we were getting everything running on the GPUs with optics and trying to be super fast there, one thing that we run into is it's actually quite expensive to JIT for the GPUs. And so there's in the GPU drivers, there's a facility where that generated code has a cache that lives underneath, so that it's not fully incurring the expense every time if it's a shader it saw before. But one of the ways that we were thwarting this cache is that our implementation of strings, the nature of them being a pointer to the characters is that might not be the same value every time that it runs. And so to the extent that those were trying to get baked down into the code we were sending to the GPU as constants, that was making it have cache misses. So by switching to a completely deterministic hash of the strings as the main representation that we're using on the shader execution side, that makes it much more stable from run to run and was a big improvement in the GPU compilation performance. Another thing I will not give much detail on right now because Curtis has a whole talk coming up in about 10 minutes. But we extended the APIs for the various kinds of free functions that we use, particularly on the GPU, but this is a preferred way on the CPU as well. There are a number of advantages, and especially this interesting facility for building getter functions for get attribute. Curtis will talk about that. In addition, there are just like countless little improvements, especially things that have performance impacts for people using the SIMD batch shading backend and especially optics. Next. Great. Even though this just happened last spring, we are on the verge of moving to OSL 1.15, and this is going to be a short release that is, maybe a little less feature rich than normal because we know it's a short time span, but what we're trying to do is shift our release cadence back to the fall so that it corresponds to a number of the other packages in our ecosystem instead of being out of phase with all of them. So even though it's a light release, we want to get back in sync with everything else. So the current proposed schedule is that we're going to try to branch for this release and declare a beta around September 1st with the hopes of it being stable pretty quickly and start this as the supported release family on October 1st or as soon as we're able to do. Yeah, great. So what's coming in this release? Yet again, we are raising some of the minimum dependencies, much less extensively than the last time around, but the notable ones are that we're going to drop, unless someone has a really important objection, we are dropping support for Python 3.7 and moving to 3.9 as the minimum. And because our supported LLVM releases had such an incredibly wide span, we're going to pull those up from 11 being the minimum to 14 being the minimum. And this allows for a lot of code simplification because the LLVM changes their APIs and features on quite a regular basis. And so when we have to support too many different versions of LLVM, this sort of litters our code with a lot of, multiple code paths and conditional compilation. And it really makes it difficult for us to have a good testing matrix that we are confident is testing against every possible version. So we're tightening that up. Another big feature coming this time is the BSDL library. I will let Alex speak to that. We have a whole section on that coming. And we are continuing to push forward with phasing out the old renderer services class for more reliance on what we're calling the free functions. And again, Curtis will address that. And then the last sort of build and test improvement that we have is right now our CI is building on Windows, but not fully testing, but we're getting really close. So I hope that by the next time you hear from us, we can confidently say that every PR is being fully CI tested, built and tested on Windows as well. That will be a long time coming big relief for us to know that we never integrate anything that is going to break on Windows. Next. Great. So a little bit about this, how to get involved as a project. Oh, Chris, is this part of you, or did you want to, should I just keep talking?
You can go, yeah.
Okay, yeah. So just so everybody knows, so every second Thursday at 2:00 Pacific time, we have the technical steering committee meeting. The TSC members come, but it is an open Zoom meeting like all of the other ASWF activities. Everybody is welcome to join. Everyone is welcome to speak. We do want to hear your opinions. And it's actually quite rare that anything comes up that requires any kind of formal vote where we really care who in the meeting has a real TSC seat and who is just there to participate. So yeah, please do come. Also on the Academy Software Foundation Slack instance, there is an open shading language Slack channel. To find all the channels there, there's actually a whole lot. You need to like do the thing in Slack where you can browse the different channels available. But there is one for open shading language. And also, of course, on our GitHub, that is where a lot is being discussed in terms of the PRs and issues and discussions. And then the last thing is Dev Days. I think there's another slide after this. Yeah. So Dev Days is a ASWF wide activity that is basically like a 24-hour hackathon meant to give people an excuse and extra support to try to make a small patch into one of their favorite open source projects as a way to do something new, to contribute to the project, to get integrated into that community, to learn about how some important software that they rely on works internally, and feel like they are empowered if they see an improvement that can be made to go ahead and do that. That's the point of these all being open source. So please participate. And if you are a leader in one of your companies, I urge you to scout out the people working around you who maybe haven't participated in open source yet, but it would be a good professional development opportunity for them, as well as kind of a risk mitigation for your own company to know that you have more people who feel like they could go in and fix or improve something in the open source projects that you rely on. So this is not just for open shading language, it's for all the ASWF projects. We have done it 3 times now, and so we're starting to really get the hang of it and do it multiple times a year. The next one coming up is September 25th. So keep an eye on the ASWF website to stay abreast of it. If you're working for a company that hasn't done it before, it is not too early to start the processes of getting the right permissions and CLAs signed and things like that. Sometimes they require a little bit of lead time. I felt like there was something else I wanted to say about that, but I don't know. So let's move on. So the next guest speaker is Alex Conti from Sony ImageWorks, who is going to talk about the BSDL. Go ahead, Alex.
Yeah, this is Alex. Next, yeah. So BSDL, yes. I will admit it's not a very clever name. It's something that contains BSDFs and it's a library. So we didn't break our brains. And we name it like that. Next slide, please. So in this talk, I'm not going into details of what a BSDF is, because if you're listening to this, you are probably familiar to shading languages. Also, it's even worse than that. You may be a render developer and you work maybe on your own render or at some studio, some in-house render, or a commercial one, or a video games, or all of the above. And you are perfectly familiar with what a BSDF is. But for the casual listener, I would say that a BSDF basically describes how a surface reflects or transmits light, is what makes glass different from metal or fabric and all of that. Yeah, next slide, please. And so every render out there has its own collection of BSDFs, a whole catalog that offers to the shaders. And normally it looks like this. There is a parent class, which is usually called BSDF, and this is an abstract interface. And from there, they inherit and they specialize specific types like metal or diffuse or whatnot. And to the render, this BSDF object is an opaque thing. Basically, offers two methods, two main methods. Next slide, please. So yeah, this is the 2 key pieces of a BSDF. The eval method takes an incoming direction and an outgoing direction and computes the amount of energy that gets scattered towards that direction. This is what determines the appearance of the material. And if you're writing a path tracer, backward path tracer, you also need a very important method as well, which is sample. This method is taking up, maybe call it a viewing direction or outgoing direction, and a bunch of random numbers. And it's going to compute a incoming direction with a probability which is or should be proportional more or less to the eval function. This one is the one that determines how clean your render is. The closer it resembles the eval, the less noise you're gonna get. So next slide, please. And that's it, you're ready to go. If you implement those two methods correctly, then water will look like water, fabric like fabric, wood like wood, and you're good. Yes, you also need to handle tons of geometry and tons of texture data and complex lighting, a full production render, but and on top of that, of course, a bunch of very talented artists to drive all of it. But other than that, you're all set. Except the API that we just saw is a little bit simple. Usually there will be more. That a render typically would use ray types, have its own types for colors, vectors, and hacks, artistic controls, and whatnot. So the key question is, next slide, please. So how can an external BSDF library work for you? I mean, we are trying for it to work for everybody or for most people by being as flexible as possible. So BSDL is a template library. It lets you choose what is your base type for BSDF. It lets you wrap an existing law with whatever decorations you need or type conversions. It's also a header-only library. Everything's inline, and it depends only on iMath. It belongs to OSL, but it doesn't even depend on OSL in the sense that you don't have to link to anything else. You probably are linking to OSL already, so you don't care. But in fact, you could just copy the directory, and that would still work. Or you can just keep a built-in dependency. Next slide. Yes, thank you. So okay, so let's imagine that there is a particular BSDF lobe in the library that you want to use in your render. This is how it works. You basically take that particular lobe, you create a thing wrapper. It's another type, just very simple type, inheriting from that lobe, and then you tell that lobe to inherit from your parent BSDF. And this way you insert this BSDL lobe into your hierarchy, your structure, and the render talks to the lobe through the wrapper. So you are in full control of what it's doing. Next slide, please. Let's see what we did in test render. Now, keep in mind that BSDL was not developed for test render. It was developed for ImageWorks in-house render, and this is how we integrate it in test render. So this is pretty much what I said in the previous slide. There is three things here. Well, first of all, this code snippet is almost verbatim from test render setting.cpp. And it's creating a new type, MX conductor, inheriting from the BSDL lobe. And we also tell that lobe what is the base class that we need to inherit from in test render, which is called surprise, surprise, BSDF, right? And then the rest you have to do is just override the eval and sample methods. In this case, it's a very simple forward to the base class implementation. This is the simple way it was in test render. So next slide, please. Okay, so other than providing specific BSDF implementation that could be more or less interesting, what else, as a framework, what else does BSDL bring to the table? Well, it's, like I said, it's a header-only library, everything's in line, so it's good for the GPU. You can override the fast math functions that it uses if you don't like the existing ones, and it can work both in RGB and spectral rendering. If you want spectral rendering, it's going to use the hero wavelength approach, and you can switch. I mean, it works at runtime. you can have the same binary rendering in both modes if you want, of course. And it also includes the usual production tweaks like visible normal correction, bump normal shadowing, roughness regularizations, and a few more. And this is the last but not least that I wanted to highlight is that we build albedo tables at build time for every for any BSDF that needs to. And this is very handy for those BSDFs that need some kind of multiple scattering energy preservation thing. It generates all those numbers, like it runs a short integration to generate the numbers, puts those in static arrays and in a header, so it goes automatically to CPU memory and GPU memory. You don't have to do any stuff. It's very neat. So yeah, next slide. Oh, there's one more thing, very interesting, which is, on GPU, we don't have virtual methods. So normally when you want to implement polymorphism, what you usually do is to have switch case statements, which is very cumbersome to write by hand. So there is this very neat idea I took from PBRT. So thank you guys. It's a template class, a helper class that writes for you the switch case. Just look into test render the way we use it there, because I will not talk about that in detail here, but it is very handy. It saves you a lot of boilerplate code. Also, you get, if you want to use spectral, you get up and down sampling, conversions from RGB to spectral and back. It's also part of the library. And finally, very important for us, is that every BSDF comes with a method that gives you a description of the input parameters that you can easily use to register all your BSDFs with OSL as closures. So the shader, it has those available. Next slide. Oh, and by the way, we are open sourcing all our BSDFs that we use in production. That is just a bunch of the typical things, thin layer dielectric, clear code, metal, some sync closures, even hair closures that we use. I will not go into detail, but this code is exactly the code that we use for our final frames. It's not a simplification, nothing like that. If you watch one of our movies and you see something that doesn't look right, you can try to find a bug in that code because it's what's running in our render farm. Next slide, please. Oh, and we're starting with Material X, by the way. So Chris told us that there are reference implementations in test render for every BSDF the Material X uses. So we're trying to, one by one, try to promote those to BSDL and give them a production-ready implementation. We recently implemented the conductor and dielectric with multiple scattering energy preservation. Check it out if you're interested. And next slide, please. Because our plan with Material X is that we want to switch production to Material X. We are not using Material X today, but we want to make, my plan is to make the BSDFs for Material X good, much better than what we have on the SPI collection. So we convince easily, say the writers and artists, to switch to this. And everything that we do is going through BSDL. So you're going to see what we're doing there live. Next slides, please. And yeah, well, we want BSDL to be successful because we want to be open about our tech. We want to encourage other studios and maybe academia to jump in there and participate. Every render is different, but the BSDFs, they all look the same. And we would love to get even contributions from papers and things like that. We want to make it easier for us to switch to Material X, also make it easier for everybody else to use OSL and Material X. And also we want to make it easier to work with us, with ImageWorks. This is how we sold it to legal. So thank you, Larry, by the way. Next slide, please. So, okay, you may think this sounds good. So you go in there and you look at the code and you think, oh, this design just doesn't fit my needs, for some reason doesn't work for you, please let us know. Let us know how to remove blockers, or even better, submit pull requests, make suggestions, anything. You may have better ideas to do what we do. Please contribute or pull request it. Of course, there's a lot that could be simplified and cleaned up. Take into account that a year ago, this library was so deep in our render, it was impossible to extract it. So it was a lot of work to just remove all the dependencies and leave only iMath and just put it for the public. So there's a lot of stuff that can be improved and cleaned up. Oh, and don't be set back by the spectral thing, because if you just want to do RGB render, you're good. I mean, the spectral stuff doesn't change the BSDF code significantly. And if you hard code the hero wavelength to 0, all that conversion code goes away from the compiler, and you don't pay for it. Finally, I want to give thanks, of course, to Chris Kula. We developed most of these BSDFs together back when he was at ImmersWorks before he moved to Epic Games. And of course, Larry Grith, he made it possible. He made it possible for us to open source everything and made us a spot in OSL, what made OSL to begin with. And of course, give thanks to the ImmersWorks bunch, all the engineers and artists. This is a big team effort. And I think that's all I have to say. So thank you very much for listening.
Okay, and next we're going to have thank you, Alex. We're going to have a talk from Curtis Black from Netflix Animation. He couldn't be here live, so he kindly recorded his talk in advance for us. So I'll just play the video now.
Hello, everyone. I hope you're all enjoying Open Source Days. My name is Curtis. I am a software engineer on the rendering team at Netflix Animation Studios, and I'd like to give an update on the renderer services bitcode work that has been done over the past year. So a big thank you to everyone who's helped here. Larry, Alex, Stina, Luke, Thibaut. I'm sure there are other people who have contributed to this prior to me joining the effort, so apologies if I missed anyone. But if you're a renderer developer not already using these features, I hope this can also be a bit of a guide about how to get started. So the renderer services bitcode is the new way for renderers to implement the functionality that OSL needs to run shaders. The way it works is that a renderer will compile parts of their code into a module containing the LVM intermediate representation of that compiled code. This module is then passed to OSL at runtime. Then when OSL compiles shaders, it will link and optimize against this module. So essentially, the shader code and your module code are thrown together in one soup, and then the target specific code, x86 or GPU, is generated from there. So while the current approach would link shader calls into your renderer code, this new approach allows the renderer code to be involved in the shader optimization process. So the code that the renderer puts in this module are the renderer services free functions. So this part is fairly straightforward. Basically, all of the existing C++ virtual functions you would implement by inheriting renderer services, they're all replaced with standalone C functions. They're all prefixed with rs underscore to make it clear which ones you need to implement. They have tags like rsop for declaring C linkage, host device for GPU compilation, but mostly they are the same as what they would have been on the renderer services class. So in this case, get matrix, the virtual function is replaced with rs get matrix. And because C doesn't have type-based overloading for functions, we have rs get matrix space time for this particular overload. Why would we want to do this? Well, there are multiple benefits for this. The first one is that we want to provide an official API for GPU renderers. So we need GPU renderers to be able to extend OSL without using virtual functions. And this should remove the need for all of the current patching of symbols like OSL functions. And the idea is that they'll still stay private, and the rs underscore functions will be the official API that you can extend from. If you're writing a CPU plus GPU renderer, then you can take this one source code and cross-compile it for both, which is a nice feature. And an interesting one is that now your renderer code can be included in the JIT compiler optimizations for each shader. So let's have a look at that. All of the examples here I've taken from test shade and test render. So in some cases I couldn't fit them all on the slide, so I've had to cut them down a bit, but I hope it just makes it clear what they're capable of. In this example, we have a point that's being transformed into a space, the string MySpace. And if you're a renderer implementing the get matrix for this transformation, you might have a code function that looks like this, with a bunch of control flow for checking different spaces. Because this function is now baked into the shaders, the JIT dead code removal can now remove all of this extra control flow and just keep the part that it needs for this function. So it's quite an interesting way of doing things now. Before, your renderer would be optimized at compile time, your shaders would be optimized when you run them, and there would be a barrier between the two. This allows you to control where that barrier is and how much of your code in the renderer can be seen by the shader optimizer. So where we're at currently is that most of the API is now implemented and merged in the 1.14 release. There are some things still in code review, which we have to go out soon. For the most part, the function signatures are a direct match. So the virtual functions are just replaced with rs underscore, almost the same thing. We wanted to keep the update cost as small as possible. There are some exceptions though, where we needed some additional flexibility or we wanted to deprecate some unused OSL features. And if you were to take this latest release, although there would be much less GPU specific patching of OSL functions, there's still a little bit that we're looking to clean up. So at the moment, all of these functions here are being ported over. These ones are the ones which have just direct correspondence from the virtual functions to the RS functions. Not much has changed in terms of return types or arguments or anything. These ones should be the easiest to port over. We've also added some new ones. So for example, a bunch of printing with different log levels. We've added trace getting functions. So this will replace get message with trace. And we need a way to allocate closures on the GPU. So we've added RS allocate closure as well. Those are all the fairly simple ones. It gets a bit more complicated for get attribute and for interpolated data. So in these cases, we recognized that the functions might be quite complex. They might not be, small amounts of control flow. They might have a lot. So in this case, we wanted to reduce the amount of JIT work that has to be done to compile each shader. So we've implemented builder functions. So this is a two-step process now. OSL will tell you everything it knows at JIT compile time about a get attribute call or interpolated user data retrieval. And you can build a function which is optimized for that use case. Then you tell OSL what that function is. And so this offloads a bit of that JIT compilation work, which might slow down shader compilation, where you can provide specific targeted ones for each of the use cases you need to support. These ones are opt-in as well, so you return true from the supports function if you want to opt into these ones. So let's have a look at that, because this one highlights some of the performance gains you can get from this system. So here is an attribute getter, a build attribute getter. It's the same for interpolated attribute builder as well. The concept is similar. The builder is provided with all of the arguments that the original get attribute function would have been provided with. The only difference is some of them are now pointers. The ones which are pointers are the ones which may or may not have JIT compile time information available for them. So if, for example, the attribute name passed to a get attribute is fully dynamic, it can't be known at compile time, then this will be null. We don't know it. But if it is a constant, like for example, in the previous example, the MySpace string was a compile time constant, OSL will tell us here. And so we can build a function specifically for that use case. An example of how you could use this, for example, is if you are looking for a primvar your get attribute, you might be able to use that, do that map lookup here instead. Find the offset and size of that prim var on your hit object at shader compile time, and then bake that offset and size into your shader. So these functions here, rs get prim var, you can provide in your module, and you can build that function with a specific offset and size. Then that offset and size will be baked into those functions when they get merged into your shader. So for example here, this get prim var, notice it doesn't have the name anymore. We've removed the name lookup, done that at shader compile time, and then the render time access of this is just a mem copy from where your prim var is into the OSL memory space. But of course, you can still continue to rely on the dead code removal that OSL would do itself. For example, if you wanted to do your prim vars with this mem copy approach and camera attributes with a bunch of control flow, you're still free to do that. So if you'd like to get started with this stuff, the examples again are in test shade and test render. But basically, we provide some CMake helper functions for you to do this. So you can include these functions that we provide in OSL. You define all of your free functions in a C++ file. You compile them with this macro, and that macro will embed the compiled module into your library sources, which then you can link into your renderer library. Then when you set up OSL to run the shaders, you can tell OSL about where this module is. And so here we've got the external linkage for that module, which is done by the CMake macro above. And of course, you can do the same thing for each target that you want to support, different GPUs, for example. So a few things that I've noticed while implementing this in our own renderer glimpse is that the CMake configuration and compilation can be a little bit tricky to set up. So it is worth spending some time making sure that all of your build flags are consistent between how you build your renderer and how you build the free functions. The function names and types must match exactly. These errors will show up at runtime rather than at compile time, so they're a bit trickier to find. And also linker errors can just be a bit more cryptic than compiler errors. So I'd suggest just copying the definitions from OSL and then implementing them in your renderer. And then lastly, an important one to be aware of is you now have control over how much dead code removal the JIT can do, or rather has to do. And this has trade-offs for compiler time and code duplication. So you might want to consider how much code you're including. If you want to include your whole texture system, that would provide OSL with the most information to optimize on, but it would also increase the compile time and code duplication. You might instead prefer to make these functions extern, not optimize them into the shader, and then link them in later, for example, using this register JIT global or using pipeline linking, or anywhere on the spectrum between these two things to optimize the trade-off between performance and compile times. So yeah, I hope this has been a useful intro to the free functions. If you've got any questions, please look at the test sheet and test render. They have all of these examples in there, or reach out with any questions. Thanks for listening.
And that's the end of our pre-program part. I think we might have a minute or two for Q&A, but while you're thinking about that, we have called out a few other town halls and DigiPro and SIGGRAPH talks that are related. So you know, check these out. Often they do have OSL related or OSL adjacent content. I'll call out the last one. Just an hour ago, I heard the practice talk for the Sony GPU material, and it's super great and is very along the lines of some of the details of how we integrate the shaders into our GPU path tracer. So if you're a renderer implementer, you'll probably find that pretty interesting. And I haven't seen the Pixar talk. I bet that one's great too. Yeah, any questions? We a couple minutes.
I'll just mention that's on Tuesday. I think the Sony talk is at 4 p.m., something like that.
All right, well, you all know how to reach us usually, the OSL Slack on the ASWF Slack instance, the mail list, GitHub, and our open Zoom meetings every second week in this time slot, but 1 week out of phase from where we are now. Great to see you all. This was recorded, we sure hope, and should be up on YouTube with the rest of the virtual town halls shortly. I don't know exactly when, but keep an eye on it. And yeah, everyone that I've been to so far has really been great and full of good information. So I encourage you to look at them for all of the projects that you're involved with. Thanks, everybody.
Thank you.
Thanks for joining.